Right, if you can turn to page 9. So this is still a integral topic, but what's different here is now these are problems that involve bounds that are either at a discontinuity or there's a discontinuity somewhere inside the interval, but we can still sometimes able to find integral even if we're going, let's say, going to infinity, or if there's a vertical asymptote involved. So we call these improper integrals because there's something off about the bounds in terms of continuity. Okay, so improper integrals are integrals with infinite limits of integration or have an infinite discontinuity, like a vertical asymptote on the interval. So let me just provide a couple of examples so you can kind of see. So for instance, integral from 1 to infinity of 1 over x dx is considered an improper integral because we see a bound that is going up to infinity. Here's another example, integral from -1 to 1 of 1 over x dx. This doesn't seem like something that we would consider as improper integral. However, the reason why this is because between -1 and 1, this graph is experiencing a vertical asymptote at x equals 0. So because there's a discontinuity in between the interval, we consider this an improper integral, and there's certain steps we have to involve when there's a break, some on that continuity break in that interval. So the way that we're going to handle this is, let's say our function is continuous on the interval from a to infinity. Then the way we handle this integral from a to infinity is we're essentially going to involve that infinity. We're going to find the limit as b approaches infinity, and then go from a to b of f of x dx. So we're just basically going to handle the problem like we normally would, right? So ignore the bounds, take the antiderivative, plug in the upper and lower bound, and that b, we're going to let that b represent, or let that upper bound be represented by a variable b, and then we can eventually push that b out to infinity and use our knowledge of limits to help us decide, okay, is that going to converge at a real number, or is that going to get pushed out to infinity? Same process here. Let's say we have the lower bound being that has the infinite limit. Then we can say limit as, again, we can use any variable. Sometimes I choose between either a or b, really doesn't matter, but a approaches negative infinity, and then integral from a to b of f of x dx. All right, so let's see if we can work through some of these problems here. So let's say we have integral, definite integral from 1 to infinity of 1 over x to the 4th dx. We see infinity as our bound, so that's obvious that we have to involve this process of improper integrals. So we'll say limit as b approaches infinity from 1 to b of 1 over x to the 4th dx. So really, we're kind of working from right to left. We're going to take the antiderivative, then plug in the upper and lower bound, and then finally push b out to infinity and see if we can make a conclusion in terms of what our definite integral is going to be. So let's just handle the 1 over x to the 4th first. We know that this is not going to be a natural log rule. We'll only do natural log if it's x to the first power in the denominator. If it's any other power, we got to bring it up and go through the power rule. So let's get it ready for our power rule. All right, we'll go ahead and apply our power rule. Add 1 to the exponent, divided by the new exponent. So now that we have our antiderivative, let me clean this up. Half bracket, and then we can start involving our bounds. So b is eventually going to be pushed out to infinity, but right now we're just going to let a variable hold that information. Okay, so upper bound minus lower bound. Okay, so now that we've evaluated our bounds, let me put that limit notation in front. So we're going to now think about what is happening to this fraction if we were to push b out to infinity. So if we push b out to infinity, this denominator is getting larger and larger, which is going to cause the entire fraction to get closer and closer towards what? 0. Yeah, so we know this is going to zero out. If this zeroes out, 0 plus 1/3 is equal to 1/3, and this is a real number, so we say that our area converges to 1/3. Usually, if your b is left in the numerator, that's going to cause a fraction to go out to infinity. If it goes out to infinity, then we say that our area diverges, and we don't have a real number. But in this case, we do have a real number. I do want to point out that it seems strange, though, that if something is going out to infinity, how are we able to find the area if it keeps increasing? So the reason why we can find an area, even though this keeps increasing out to infinity, is because this is showing us that there's an obvious ceiling. So what's happening is, yes, the area keeps increasing, but imagine it was like 0.3, then 0.33, right? Yes, it is increasing. However, there's a noticeable ceiling. It's increasing, but the ceiling is obvious that it's getting closer and closer towards 1/3. Other times, though, we're not able to spot a pattern, and it just continues to increase without bound. If that's the case, then we're going to be able to conclude that our limit is going to be infinity, or the integral doesn't exist. But in this case, this limit is telling us that it is continually increasing, but it's increasing in a very predictable manner, getting closer and closer towards 1/3. All right, so if the limit exists, the improper integral is said to converge. If the limit does not exist, then the integral is said to diverge. Okay, so let's look at an example where there could be a diverging solution. So 1 over x dx, again, we see improper integral because of the bound that's approaching infinity. So we can rewrite this limit as b approaches infinity. And again, you can use any letter that you want. I think the book just has it using b, but you don't have to use that. So we're going to go from 1 to b of 1 over x dx. Now this one is going to be natural log because this is a variable to the first power in the denominator. So let's just go ahead and evaluate that antiderivative. 1 over x dx becomes natural log. evaluate it between 1 and b. Upper bound gets plugged in, natural log of b minus natural log of 1. Okay, so now let's evaluate the limit of our resulting expression. So here, if we were to plug infinity in for b, what's going to happen to this value? Yeah, it's going to continue rising. I mean, it's growing at a very slow rate, but it is still increasing up to infinity. Infinity minus 0 is still going to be infinity. And so this, we say that our area is going to diverge, or basically no solution. So infinity or diverges. So both of these graphs have a decreasing look to it. However, the reason why this converges and this diverges is because this is closing in at a fast enough rate where the increase is predictable, that the sum of all those areas is decreasing to the point where we can obviously see that there's a ceiling. In this case, it is closing in, but it's not closing in fast enough. And so the area keeps increasing without bound. And so we can tell that that's the reason why our series diverge, or our area diverges. And this is a bit of an extension into what we're going to see when we talk about infinite, when we talk about series 2 units from now. So anytime we have this form where 1 over x to the p, we're going to be able to, this function is going to be able to diverge as long as our p-value is greater than 1, where we're going to be forced to use power rule. However, if p is less than or equal to 1, then this graph is not going to close in on the x-axis fast enough and is going to continue increasing without bound. Okay. All right, next page, page 10. All right, let's look at some more instances of improper integral. So remember the depth integral a to b f of x requires the interval to be finite in the first theorem. First fundamental theorem of calculus requires that f of x is continuous on the interval from a to b. If the interval does not meet these requirements, we need to manipulate the problem in a way that can work for us. So another form of improper integral is if we're going from negative infinity to positive infinity. If that's the case, what we need to do is we need to write it as the sum of 2 improper integrals and let one of the bounds be an anchor point. So an easy point that we would like to choose, that we'd like to start off with, is 0. So if we're going from negative infinity to infinity, we can break it up into 2 separate regions, negative infinity to 0, and then from 0 to infinity. It doesn't always have to be 0, but I think 0 is a good starting point. It's also easier to plug in, so usually that's what we do. It's easiest to use 0 if possible. Okay, so if either of these integrals diverge, then the whole diverges. So that means we can't say, oh, one diverges, the other converges. We can split the difference. If one diverges, the whole thing will diverge. All right, so we have the integral from negative infinity to positive infinity of e to the x dx. So let's go ahead and split this up into two improper integrals. In both improper integrals, we want to have one of the bounds being a real number. So let's go from negative infinity to 0. And then we'll pick up at 0 and go to infinity. Okay, so we're taking this extended boundary and splitting up into two smaller boundaries. Okay, so let's set this first one up here. So let me use A for this in negative infinity. And then separately here, I'll use B. So the nice thing about e to the x is the integral is just e to the x. There's no need to have to go through use substitution since that x is not anything more than just that single variable. So we're just left with e to the x as our antiderivative. Evaluate between upper and lower bounds. So upper bound, e to the 0 minus e to the a. And then we'll evaluate this limit here. Limit as a approaches negative infinity of e to the 0, which is 1, minus e to the a. Now, e to the 0 is 1. E to the a is e to the negative infinity, and negative infinity allows us to push this base to the denominator. So I can make this 1 minus 1 over e to the infinity. And what does this tell us? If I have 1 over e to the infinity, what's happening to this fraction? Getting smaller towards 0. So this does converge to 1. But that's only half of the problem, right? We have to also show that this converges if this whole thing is going to converge. So we'll box that off and work on the second portion to see if this will also converge to a real number. Okay, so e to the x becomes e to the x again. Evaluate between 0 and b. Sorry, I was using a, yeah. Okay, so this is now b. So I have e to the b minus e to the 0. However, in this case, if I plug infinity in for b, e to the infinity is gonna do what? Infinity. So infinity minus 1 is still going to be infinity. So you have one side going to infinity, one side going to 1. If there's anything that is going out to infinity, the whole thing is going to diverge. So we say that our answer diverges. If one portion diverges, the whole integral diverges. Sometimes one of the bounds is sitting at a vertical asymptote. If that's the case, we can still involve integral. We just have to involve one side of the limit. So for instance, let's say it says the function is continuous from a to b. So let's say the graph looks like this. On the left side, it's continuous. However, let's say there's a vertical asymptote at b. So everything between a and b is continuous, except at or up to b, and at b there's a vertical asymptote. So let's say they're the graph doesn't exist at one of the bounds, then what we can do is we can say that we're approaching B from the left side of B. And we can say this limit. I'm going to use a different variable since A and B are involved. So I'll use T approaches B from the left side of B because the graph is existing to the left of B. So we're approaching B from the left side of B. Integral from A to T of f of x dx. So basically, we would approach the problem the same way, evaluate the bounds, and then do a one-sided limit and see if that can help us make a conclusion as to whether we're going to get a real number or a diverging solution. The other scenario is where the asymptote is out on the left side and the graph extends to B. So let's say the graph looks like this. There's an asymptote at A, and the graph extends, but then it's continuous all the way through. So if there's a break on the left side, then we'll say limit as T approaches A from the right side. The reason why it's from the right side is because the graph is to the right of A, and we're approaching A from the right side towards that asymptote. And then integral from T to B of f of x dx. So here we're just using an arbitrary variable to hold the fact that A is moving towards that vertical asymptote. Okay, so this instance would be where the vertical asymptote is at x equals B. And this instance will be where there's vertical asymptote at x equals A. Okay, so let's look at example 4. We want to find the definite integral from 0 to 2 of x plus 2 over the square root of x squared plus 4x. There is an issue in the denominator. Just by looking at this function, we know that whatever causes the denominator to be 0 is a discontinuity. So if I were to ignore the square root and just look for factors in the denominator, I'm going to get x parentheses x plus 4. So if I set the denominator equal to 0, I'm going to get x is equal to 0 and x is equal to -4. So that tells us at the very beginning that we do have a vertical asymptote at x equals 0 and x equals -4. Now, -4 is not going to impact our interval because we're only looking at the region from 0 to 2. However, there is a break at one of the bounds, so we have to take into account that that we have to approach this asymptote. We can't start at 0 since the graph doesn't exist at 0. So we'll set up our integral and we'll say limit as t approaches 0 from the right side of 0. The reason why it's the right side of 0 is because our graph is existing between 0 and 2. So if we want to approach that asymptote, it's going to be from the right side of 0 towards that asymptote. Right? And then we'll go from t to 2. I'm just going to set the problem up for my next step. I'm going to rewrite that radical as a parentheses. Okay, so this is going to be a U substitution problem. We can identify our U value to be what's inside the parentheses. And go through our U substitution process. I'm going to rewrite it in factored form because we can see that if I can get this to match, I'm able to cancel them out. So after u substitution, we're able to get the x plus 2's to go away. There is a leftover 1/2. And the rest is power rule. Remember, and even though we do see a u in the denominator, we can't go through natural log because the exponent only works if it's exponent to the first power. So we got to bring that u up to the top and get it ready for power rule. Okay, so apply power rule. U to the negative 1/2 becomes u to the 1/2 over 1/2. Do some cleanup. Dividing by 1/2 is the same thing as multiplying by 2. These will cancel out. Right, replace the u back in terms of the original variable, and then we can work on our bounds. Upper bound gets plugged in first. 2 squared plus 4 times 2, that's 4 plus 8, that's 12. And then we can do our limit as t approaches 0 from the right. Now, even though we're approaching 0 from the right, remember, whenever we're evaluating, we always plug in the real number first. If only if we see that we're getting something that is not quite where it's undefined, then we can involve decimals and plug in numbers from the right side of 0 to see if we can make a conclusion. But we always want to test the real number first. If the real number works, then there's no need to go any further. So in this case, if I plug 0 in for t, I get 12 to the 1/2 for the first term, minus and then 0 to the 1/2. That is a real number, so we don't have to evaluate any further or take any additional steps. We can just use 0, and 0 is going to leave us with a real number. So it's just root 12 minus 0, which is root 12, or 2 root 3. So we're able to show, even though there's a vertical asymptote at 0, after our evaluation and the fact that we're approaching 0 from the right, we're not getting any issues. This is going to converge. Okay, number 5. If the function is continuous on the interval from a to b, except that there is some c where there's infinite discontinuity, then we have to break our problem up where that vertical asymptote is interfering with our interval. So I have to say, though, that these are hard to spot because if you see an integral problem, you're just naturally going to want to go through the whole process. But here we see that 1 over x, there is an issue. 1 over x on its own already has a vertical asymptote at x equals 0. And then our bounds is from -1 to 1, so it's going to span across that asymptote. And normally we can't find the integral if the function is not continuous. So the way that we're going to work around this is we're going to break it up into 2 separate integrals, -1 to 0, and then from 0 to 1, and then we'll use one-sided limit to work around that asymptote. So we're going to go from -1 to 0. of 1 over x dx, and then pick up at the asymptote and go from 0 to 1. Now, we do have to make some adjustment further on because we know that there is an issue at 0. So basically, this is what the graph looks like. Just to kind of give you a visual here. 1 over x looks something like this. So we have to figure out, is there an area that can be found on this side from -1 to 0? And then can we figure out an area on this side from 0 to 1? Okay. However, there's an asymptote, as you can tell, at 0. So we have to rewrite this integral with one-sided limit since 0 doesn't exist as on the graph. So we're going to say limit as t approaches 0 from the left side of 0, since this graph is on the left side of 0, headed towards that asymptote. And then on this side, we're going to go from 0 from the right to 1. So this side is limit as t approaches 0 from the right side of 0. Since we're starting here and we're headed towards 0 from the right side of 0, integral from t to -1. Okay, we'll handle this one at a time. Let's work on this left one first. 1 over x becomes natural log. Let's evaluate it between t and -1. So this is an instance where if I try to do natural log of 0, natural log of 0 doesn't work. But I can pick points on the left side of 0, let's say -0.1, -0.001. Now, normally we can't do natural log of a negative number. However, there's an absolute value here. So this is the same thing as saying 0.1, 0.001, 0.0001. And natural log of a value closer and closer towards 0 is going to push it out to infinity. And because this already goes out to infinity, we know that we can stop and say, okay, if one side doesn't converge, the other side it doesn't really matter what the other side is. And so if you can show that one side is already diverging, you know that your full integral is going to diverge as well. We're not able to show that this is going to approach a real number, so we can stop and say that this integral is going to diverge. So when you see an improper integral, whether there's a vertical asymptote or infinity, you just have to set up using limits in the front. But you're going to start the problem the same way that you would with other integral problems. You're still going to identify the appropriate integral rule, plug in your upper and lower bound, and at the very end, then you evaluate your limit and see if you can convince yourself whether it's going to be a real number or it's going to be infinity. If it's a real number, then we say that our integral converges to that number. If it goes to infinity, then we say that our integral diverges. Okay. Okay, number one, on page 11, the integral from 1 to infinity of 1 over x squared. There is a vertical asymptote at 0, but you can tell that 0 is not going to get impacted by the integral. The boundary does not involve the vertical asymptote, so we just ignore the fact that there's an asymptote at 0. However, we have to pay attention to the fact that there is infinity involved. So we can just say limit as b approaches infinity. We'll let variable b hold that information where that upper bound is going to be pushed out to infinity. So we'll go from 1 to b. And I already know that this is going to be power rule, so I'm just going to bring that x up to the top to get ready for my next step. All right, no natural log if your variable is raised to a power other than 1. Okay, so we're ready for power rule. Do some cleanup. And then work in your bounds. And now imagine plugging infinity in for b, and let's convince ourselves, are we going to get a real number or are we going to be able to converge? So if you imagine plugging infinity in for b, what's going to happen to this fraction? 0. And 0 plus 1 is equal to 1. That's a real number, so our integral is going to converge. All right, 2 over x squared plus 4x plus 3. We can't expand. Looks like use substitution is not going to quite work either. Do you guys recognize this? What do we have to involve here? What we talked about yesterday. Partial fraction. Okay, so this is going to be a partial fraction problem because the denominator is factorable and the denominator has a higher degree. Our initial steps is not going to quite work out. So I'm going to rewrite this x squared plus 4x plus 3 as x plus 3 and x plus 1. So we'll go ahead and work on our improper integral, sorry, our partial fraction before we come back to this integral here. So we know that this fraction, ideally, we would like to get it split up into 2 separate problems to make it easier for us to find the integral rule. So we're trying to solve for a and b, and I'm going to go through the cover-up method. So set the first denominator equal to 0. You're going to cover up the x plus 3 and replace all the x's in the numerator and denominator, if they exist, into the entire fraction, and that will help us solve for a. So -3 for x, -3 plus 1 is -2. 2 over -2 is -1, so a equals -1. Okay. If I want to figure out what b is, set that denominator equal to 0. I get -1. Cover up the x plus 1 since we don't want to be plugging -1 in, otherwise we'll get 0 in the denominator. So -1 in for x, 2 over -1 plus 3. I get 2 over 2, so b equals 1. So I'm just taking the integral of -1 over x plus 3 and 1 over x plus 1. Okay. A lot easier to manage because these are just both going to be natural log. So I'm going to go ahead and evaluate my integral. So this is 1 over u du, and that's also 1 over u du, which is natural log. So I'm gonna condense this. I think it's easier to evaluate, especially with improper integrals here. So I'm going to condense this to be, we know that natural log of A minus natural log of B is natural log of A over B. So I'm going to treat this like the first term and that as the second term. So natural log of right, just using the log property that says natural log of A minus natural log of B is equal to natural log of A over B. So now that I have my antiderivative and it's condensed, I'm going to evaluate my bounds from 0 to B. Now, if we're approaching infinity, we can compare degrees, right? Especially if there's numerator and denominator. So degrees are the same. And so just take the ratio of the coefficients, 1 over 1, which is 1, natural log of 1. It's just going to be 0. And this becomes natural log of 1/3. So this is a converging value since we don't have anything, neither of these goes out to infinity. So you can either leave your answer like this, or you can convert that natural log of 1 to be 0. Either one is fine. Okay, let me see if I can finish with number 4 before class ends. So number 4, 1 to infinity, x e to the negative x. This one here, use substitution is not going to work. What does this look like? You have a algebraic with an exponential. We got to go through, yeah. So we learned first day integration by parts, but we could go through what? Because there's no logs involved. Yeah, we can go through tab method. Um, this is not going to be a nested one, so we could go through integration by parts, but I think we prefer tab method, especially if we can, if it's able to fit. So we need to identify f and g prime. You know that f is going to be your algebraic, so x, and e to the negative x is your g prime. So on the f side, you're going to find the derivative until you reach 0. On the g prime side, you'll keep taking the antiderivative. When you take the antiderivative, e to the x is e to the x, but the negative one is going to produce a coefficient, so negative e to the negative x. Another antiderivative power rule, use substitution will produce another negative, so e to the negative x. Okay, there's an alternating sign that's going to be involved, so plus, minus, plus, and then pair your diagonals together. Right, so now we have x, or negative x e to the negative x minus e to the negative x. So here's our antiderivative. We can just go ahead and involve our bounds from 1 to b, and we know b is approaching infinity here. I'm going to clean this up here and push the negative x to the denominator. It's just easier to evaluate or think about what's whether it's going to infinity or a real number. Okay, so negative b over e to the b. If we do comparative growth rates, we know exponential is growing at a faster rate than algebraic. Okay, your homework is just to finish up to page 12. Have a great day, guys. When you walk the Okay, great. Let me do that. Great, thank you.
Thank you.
Thank you. Have a good day. Bye. Thank you. Bye. See you.
What's my history of markers?
All right. See you.
It's funny, I never did these posters over here,
Uh-huh.
but my sister is getting into Bon Iver, Sufjan Stevens.
Oh, nice. That's funny.
You should have her next year, I think. Oh, Madeline.
Oh, Madeline? Okay. She'll coming into AB.
I think so.
Okay.
She's much better student.
See ya.